Good morning and welcome to this course on digital IC design. So, what is the motivation behind this course, right? What leads us to study this course? What makes it possible for us to do such a course? So, mathematically, we are given this. For example, if you want to represent a number in base 10 number system, if you want to represent a number in base 10, right? Then you know that you can write it as summation ak 10 power k, right? And all numbers can be uniquely represented by this representation. For example, the Roman numerals cannot guarantee this, right? Even representing any arbitrary number in Roman numerals is not possible, right? So the number system with the invention of 0 really sort of enabled this for us. Now, there's nothing sacrosanct about 10, right? You can do this in any arbitrary base b. So what are the values that the numbers ak can take if you represented it arbitrary base b? 0 to b minus 1, right? So nothing special about this. I can take this b all the way down to 2, right? And that gives us the binary number system where I can represent x2, which is basically the same number x in binary number system as bk2 power k. Of course, the n number of bits or the number of symbols needed to represent the same value will be much more in binary compared to the decimal number system. N will be much greater than m, right? Because I have only it's going in powers of 2 as opposed to powers of 10. So once you are given this guarantee mathematically, it is possible to go ahead and do computations in a consistent manner, right? And achieve all that we need. So it turns out that if bk can take only 2 values, then those 2 values can be called logic 0 and logic 1. So this is the motivation for general digital logic, right? And computation is really the key to efficient data processing, right? So for example, the neural networks has existed for a long time, right? It has been used for recognition and artificial intelligence in general, right? But what is it that has made deep neural networks, all of a sudden very famous now? What changed from neural networks 2 decades ago to deep neural networks now? It's basically the computational power, right? You have computers that can evaluate at monstrous speeds now, right? And therefore you are able to train really large networks, right? 150 layers with arbitrary number of hidden units in each layer, fully connected, convolution, whatever it is, you are able to train these networks, right? Of course, they're going to consume a lot of power, but you are at least able to do it because its computation speed has gone up significantly in the last 2 decades, right? And you have also been able to pack so many more transistors in a single microprocessor today, right? So what are these kind of computations? These computations are essentially, not surprisingly, arithmetic and logical, right? Everything you can just boil it down to a simple addition, multiplication, subtraction, or logical, maybe you can do ANDs, bitwise ANDs, ORs, XORs, and so on, right? So if you look at your cryptography, it's heavily using the concept of an XOR, right? You can use parity and stuff like that. So these things are ultimately, they just boil down to some logical operation which happens bitwise, or arithmetic where you do something bitwise and then start propagating the carry and so on across bits, right? In some cases like DSPs, you can also do some special instructions like convolution. That's the heart of a DSP. So in that case, you can make that a single instruction, right? So what I mean by single instruction is, in a microprocessor, you can say conv of something, right? Which means in one cycle, once the convolution is done, it will proceed to the next instruction. So those atomic instructions is what I am talking about here, right? Those are the building blocks for your microprocessor. And naturally, the question to ask is, how good is the computational efficiency? Okay, and that's what we want to improve. But then what is computational efficiency? So it turns out that this can be quantified in two ways. One is how fast, second is how much energy, right? So it's important to just keep in mind that energy is different from power, right? If I have a server that is connected to a power outlet, I don't care too much for efficient energy processing because I have sufficient energy coming from the power outlet. I just have to keep the power under control, right? So that it doesn't go out of control and heat up the processor, that's all. But on the other hand, if you're doing something on your mobile phone where you're charging on the outlet once and then you're roaming around for the rest of the day, then you have to ensure that you do your operations in an energy efficient manner, right? Because ultimately every coulomb of charge or nano coulomb of charge that's coming out of your battery is going to drain the battery out little by little, right? So how much energy is also very important, but unfortunately in this course we will not have time to go into all of those details, right? There is a lot to do just with delays, right? How fast, and just answering the question, can it be made faster, itself is going to consume us in this course. So therefore I will not have time to touch upon how much energy and stuff like that. I will focus only on delay. How slow or how fast is a particular circuit, how can it be made faster, okay? Can it be done expending lesser energy? I will allude to this a little bit when I talk about energy and power, but that will be about it in this course. So before we jump into the details of this course, I think it's important to get a feel for what a microprocessor chip looks like in today's technology, right? So today's technology, by the way, in production is 14 nanometer in 2019, right? 7 nanometer is in technology development stage. There's really no product that has come out in mass production, right? Whereas 14 nanometer has come out in the market. What I show here is basically the IBM's Power 9 processor, okay? This is a server chip from IBM. So the focus of this chip is entirely on performance. It has to do it very fast, okay? So here we are not too worried about constraining power or energy of this particular microprocessor. We are just tuning things to do it really fast, okay? What is the technology? It's a 14 nanometer FinFET SOI technology. SOI is silicon on insulator. If time permits, I will allude to that at some point. FinFET again was introduced only in 14 nanometer. Up to 22 nanometer, the transistors were just scaled down regularly, okay, and they were able to achieve their targets without much problem. But beyond the point, beyond 22 nanometer, it became difficult to contain the leakage current, right? Keeping the on current this thing. So just a order of magnitude question, if the on current is, let's say, 1 unit, what will be the off current like? Order of magnitude. It's about 1,000th of the power, 10 power minus 3. That's what a technology can guarantee. Beyond that, it's very difficult, right? So they found it very difficult to achieve this beyond 22 nanometer with the old transistor technology. They had to move to FinFETs, okay? And that is basically some 3D structure. I'll try to just tell you at least what that structure looks like at some point when I do the transistor. But let's just take it for now. In 14 nanometer, to handle leakage current, you had to go to a radically new technology, okay, which also makes technology development very expensive, by the way. Okay, the number of fabs have come down to a very small number because it's not profitable for anyone and everyone to just run a fab these days. The investment you have to make in technology to get that small gain of, performance or power is extremely high. It was not that high about a couple of generations ago. Coming from 90 to 65 or 65 to 45, not much of a difference, but now it is very expensive, okay? What is the area of this microprocessor? It's about 695 mm square. It's about 25 mm by 25 mm, right? The size of a 10 rupee coin almost. That's how small it is. And what does this contain? 8 billion transistors. Okay, so now if the on current of a transistor is a microamp and the off current, as I told you, is 1000th, right, nanoamp, why is the off current even a cause for concern? It's a nanoamp, right? Yeah? Yeah, you have 8 billion of these transistors leaking a nanoamp each, which means very quickly we are just leaking amperes of current, right? And what does leaking mean? It means that my device is not in use, it's not doing anything, right? And in spite of that, I am losing amperes of current from my power supply. My battery is getting drained that fast, right? Or it's drawing that much power, and therefore it's a big problem. Okay, so the number of metals. What is a metal? Let me just give you a quick illustration here of what the manufacturing process looks like. Right below you have the substrate, then you have the transistors. Okay, this DIFF stands for diffusion. Okay, we'll come to what those diffusions are and in some. So this is an NMOS transistor, this is a PMOS transistor, right? We'll define all that more formally in some time, right? And then you have a set of metals. So what is this transistor? That's called the front end of line. That's the first thing that you manufacture. To do something, then you start building metals over and above that. This metal region, right, the region of manufacturing, that is basically called the back end of line. Okay, so in the back end of line, they have 17 levels of metal in that microprocessor. What does that mean? Metal M1, for example, is shown here. It is connected to this green via. That's called a via, which is a contact between a metal and a lower level metal or the diffusion. Okay, this is a contact to the diffusion, the green color, right? And M2 is the metal level 2, which basically is connected to metal 1 through this blue via. What is a via? It's either a cylindrical structure or a frustrum of metal which connects the higher level of metal to a lower level of metal. Okay. Similarly, you have M3, M4 all the way to M17. So with this, you have about 17 levels of metal, right? And what you notice here is the pitch, basically, which is talking about the spacing between metals, right, is 64 nanometer for M1 to M3, right, which means the spacing, the width of the metal also has to be less, only then the spacing can also be less, right. Then you have M4 to M5, it's 80 nanometer, M6 128 nanometer, and so on. So what happens is the lower level metals, right, because you are closest to the transistor, will be used to connect transistors sitting near each other, right. So what happens is you have one transistor sitting here, something sitting nearby. I don't want to go all the way to the top level of metal and come down. I need to go as quickly as possible. So that has to happen through the lowest level of metal, and therefore, since these are short distance communication, I don't have to worry about the resistance so much. So I can make the width lesser, right, and pack more wires also at the lower levels. But as I go higher, I would have to drive, for example, the power lines or the clock lines. These actually drive a lot of current. It can drive amperes of current, right. Now in that case, I need to ensure that the IR drop on that wire is not very high, and therefore you make those wires very wide, but of course you can't pack as many of them, right. So lower level of metals for nearby communication. As you go higher, it's basically for far communication, right. And the power and clock are basically routed at the topmost levels, which is the widest metal and also very, very low resistance. Okay. So what does this look like, right? People figured out that just scaling a single microprocessor, right, a single core, and improving its frequency forever is not giving enough returns. So you had to make it multi-core, you had to distribute your computing and all that stuff. So that's what has happened over many years in the microprocessor technology. And therefore in this chip they have 6 quadrants with 4 cores each, right. By the way, all the details are in this paper if you want to read it. 6 quadrants with 4 cores each, okay, and each quadrant has a shared L2 L3 cache, right. So people figured out that going outside to the DRAM and fetching data is extremely slow. You can't keep doing that. Therefore, you needed to have some faster access. But of course, you can't have all the access to, access to all the data at one shot. You start doing something known as caching, right? And that's why you have a hierarchy of caches called L1, L2, L3, L4, and then the memory, main memory. This basically grows in size, right? But becomes slower and slower as I go the higher level of cache. So with that, they have shared L2 and L3. So L2 is shared between core 0, core 1, and another L2 between core 2 and core 3, and then you have a shared L3 cache, which is, again shared between the cores as shown here. Okay, these are memories. So it's interesting to note that I have equal amount of area dedicated to memory as I do for computational power today, right? So what does this tell you? It says that just improving computational speed is not enough. I need to have access to that data, right? And especially in today's world, I have this concept of big data and data analytics where the volume of data is so huge that there's no way I can get all of it into my processor. So you need fast memory access and then good computational speed. So that's why you see half the chip actually dedicated just to the caches. And what's not shown here is in each core you have an L1 cache. So it's actually more than 50% of the area that is allocated to memories in terms of caches in today's microprocessors. Okay, so a small portion of this is actually the compute element, which is the ALU. Very small portion, right? There are other things like the serial links, then the DDR4 interfaces, and so on. There are a lot of other things that you need to communicate to the outside world, right? But a small area in this is actually your computational part, which is doing the ALU job or some other computation as needed. Okay, now the question is, how do I design such a chip? It has 8 billion transistors, it has a lot of interconnect, right? In the interest of time, I will not do that calculation. If I just lay out all the interconnects, the metals in one straight line, right? It turns out that the length of that interconnect, can anyone guess who was not there in the last class? What is the order of magnitude of this number? Millimeters, nanometers, meters, what? 25 mm by 25 mm chip. Okay, and I have this kind of a thing. Let's say 2500 nanometer, take M7, M17, 2500 nanometer pitch. Okay, let's assume that the width also is 2500 nanometer. What do you think this net distance would be? Just order of magnitude. I don't care whether it's 11.5 or 12.3. I need the unit there. Some guess. I need a guess, otherwise I'm not going forward. Like, do you think it will be nanometers? It will be like meters or what? Yeah? Micrometers. Okay. So I urge you to go do this calculation. Just figure out if I have a wire which is 2500 nanometer spaced apart by again 2500 nanometer, right? That means every 5000 nanometers I have one wire, okay, running across the chip, which means the length of the wire is again 2500 nanometer. Just calculate the total length. It's an astonishing number. The total length is 11 kilometers in an earlier chip. So this chip is actually higher. It's in the order of tens of kilometers. Okay, so how do you even design such a chip which has 8 billion transistors, which has 11 kilometers of interconnect? You cannot possibly do this manually, right? And therefore, what do I do? It turns out that the VLSI design flow is heavily automated, right? Lot of this is just you write something known as Verilog code, then you can synthesize and get your layout, right? Layout is basically which you learn in this course, right? The eventual thing that you can ship to the foundry and say manufacture this, right? It's a set of masks that you will make, okay? Only the critical blocks are hand laid out, which in this course you will do only hand layout, you will not do synthesis, okay? So significant portion of the chip is described using hardware description languages like Verilog or so on, right? Only some select things called standard cells, I tell you what they are laid out manually. Analog blocks are usually custom designed, right? So it's like a push button now. I give all my settings, say this is my speed of the microprocessor that I need 2 gigahertz. I need to finish this operation in this time. Go ahead and synthesize my circuit. I'll just give it Verilog code. It will do it. It will do it, right? In fact, this is the design flow. I know it may not be visible to the last bench, but all I want you to notice here, you can go see the details later. You give a design specification, you do some other things, right? But at every point there is a decision box. What is a decision box? It says, is the functionality correct? If yes, then you proceed to the next state. Otherwise, you go back and redo something. Then you check, is the design routed correctly? If yes, you do something. Otherwise, you go back and do something else, right? Timing spec, is it met? If yes, then you complete the design. Otherwise, you go back and do something. So the point is, this is not a straight, unidirectional flowchart where I give something and I'm guaranteed to get an output. This loop may never converge. And that is the reason you are even doing this course. We are going into the nuts and bolts of building this microprocessor elements, right? Specifically the ALU. And we are trying to figure out how much time it takes, how we can make it faster, right? So the point is, if the design was so automated, is it not a waste of time to even study this course? Because everything you push a button and then you are done, right? It turns out that this loop may not converge, and when it does not converge, as a designer, you need to figure out why, and you need to be able to fix it ultimately. So to do that, to understand the synthesis report saying, look, I've thrown my hands up, I cannot synthesize, the tool will just tell you that. You can't just give up saying, no, I cannot get this circuit working, right? If that's the case, robots would replace your job, right? Why would I need a human being there, right? If it's an automated decision like that. So then your job is to go in and figure out what went wrong, which is the guy who's actually causing a violation, which block inside is actually consuming all the time, can it be made faster? Now to answer all those questions, you need to do this course. Digital IC design is a very fundamental digital circuit design course where we are going to deal only with transistors, okay? And that's what I'm going to think. So if you look at the design flow, you have something called a Verilog code here, right? Then you have something called a standard cell. A standard cell is basically a set of gates which are designed, have been hand laid out and given to you, and say that, look, these are my universal gates. Now you have to synthesize your circuit just with this. For example, I could have just a NAND gate here and say synthesize my circuit. It is possible, right? It's a universal gate. I can synthesize any logic circuit with that, right? But of course, it's not efficient. So you give a few more gates and say that, okay, I have inverter, NOR, NAND, and so on. And then you say that I want to make my circuit. So the synthesis block will take this Verilog and generate a circuit like this in schematic, right? In schematic, basically, it's just a netlist. It's a text which just tells you how to connect the transistors and the gates together. Then you do a place and route, and then you get the layout. That's what happens, okay? So as I told you, the loop is not guaranteed to converge. You need to know what went wrong, right? And humans are obviously more equipped to make informed decisions. And that's the reason your jobs also will be secure, at least for some time, until AI really comes and sort of takes that over, okay? So what is the core structure? The transistor, the inverter, combinational circuit design, sequential circuit design, and design of adders and multipliers. This last block is basically the thing which is going to deal with the ALU actually. How do I design my multiplier? How do I design my multiply accumulator? Right? How do I design my adders and so on, right? But I need to do all of this before I can get there. This will take, this is more or less an introduction. Unfortunately, I can't make it a prerequisite because a lot of students come here first semester, they have to take this course, right? Otherwise, I would like to spend more time on the other modules rather than the transistor, but I will spend enough time to give you the necessary abstraction to move ahead in this course, okay? Then the inverter, the combinational circuit design. Combinational circuit design is I give you any arbitrary logic and I want you to design a transistor level circuit that will implement that logic in a given time. That's what we do there, okay? Sequential circuit is basically how do I design flip-flops, how do I design latches and so on, okay? These are the learning objectives. After you're done with this course, you should be able to characterize the key delay quantities of a standard cell. You should be able to evaluate the power dissipated in the circuit, both dynamic and leakage. That's the only thing that I'll have time for with respect to power and energy, how to evaluate these numbers, okay? Then design a circuit to perform a certain functionality with specified speed, okay? Identify the critical path of the combinational circuit, then convert a combinational block to a pipeline circuit. Pipelining is another fantastic concept where you can improve the throughput of your system. How do you do that, right? Where do you go and put your flops? How do you make sure that the circuit throughput can double, triple and so on, right? Then you should be able to calculate the maximum worst case operating frequency of a designed circuit, okay? These are the learning objectives. After we are done with this course, we'll come back and revisit this to make sure that you are comfortable answering all these questions. It's also good to know upfront what this course is not about. This course is not about automated tool flow. I'm not going to take you through that synthesis flow. That's another course which Professor Nagendra is offering, but I don't think that's open to too many students because we have limitations on the licenses and so on, okay? Verilog design, it's definitely not about Verilog design. You will not write a single line of Verilog code in this course, okay? It's not about digital design in the conventional industry sense. This is digital circuit design. Digital logic design is a prerequisite, okay? You should know what a multiplexer is, what a decoder is, all those things, how to simplify a given Boolean expression, all that you should know, De Morgan's laws. These are prerequisites. So I am not going to cover any of that in this course. And it's not about microprocessor instruction design, where I try to find out what best new instruction I should introduce in the microprocessor to make it better. It's not about that, right? We are just looking at certain addition, multiplication operations and at the nuts and bolts level of the circuit, okay? These are your textbooks. Jan Rabai and Ananta Chandrakasan, you have a book called Digital Integrated Circuits. All of this is on the website, by the way, don't worry about it. CMOS VLSI design, right? Neil Weste and David Harris. So some modules I have taken from, the Rabai, some I have taken from Weston Harris. So I will be providing whatever slides I use, right, to you through the website, but don't bank on it. Please do take notes because you will not be able to follow that. Okay, that's more for my reference rather than your reference. Okay.